A new theory shows how civilizations can spread like wildfire through space. The search for extraterrestrial intelligence, SETI, has always been plagued by uncertainty. With only one habitable planet, Earth, and one technologically advanced civilization, humanity, as examples, scientists are still confined to theorizing where other intelligent life forms could be and what they might be up to. 60 years later, the answer to Fermi's famous question, "Where is everybody?" referring to extraterrestrials, remains unanswered. On the plus side, this presents us with many opportunities to hypothesize possible locations, activities, and techno-signatures that future observations can test. One possibility is that the growth of civilizations is limited by the laws of physics and the carrying capacity of planetary environments, also known as the percolation theory hypothesis. And in a recent study, the team from University of Philippines, Los Banos, looked beyond traditional percolation theory to consider how civilizations might grow in three different types of universes: static, dark energy dominated, and matter dominated. The results indicated that, depending on the framework, intelligent life has a finite amount of time to populate the universe and is likely to do so exponentially. The study was conducted by Alan L. Alinea and Cedric Jake C. Jadrin, an assistant professor of physics and a teaching associate with the Institution of Mathematical Sciences and Physics at the University of Philippines, Los Banos. The preprint of the paper, Percolation of Civilization in a Homogeneous Isotropic Universe, recently appeared online. And for their study, the team considered how traditional percolation theory could be interpreted in terms of a logistic growth function, LGF, where a population's per capita growth rate gets smaller as a population size approaches a maximum imposed by the limits of local resources, also known as ACA, carrying capacity. Percolation theory. In brief, percolation theory describes how networks behave when nodes or links are removed, wherein they will break down into smaller connected clusters. The first known instance of this theory being applied to the Fermi paradox was perhaps made by Carl Sagan and William Newman in 1981 in a paper titled Galactic Civilizations, Population Dynamics and Interstellar Diffusion. They argued that the reason humanity has not encountered extraterrestrial civilizations, ETCs, is because interstellar exploration and settlement are not linear phenomena. In contrast to the Hart-Tipler conjecture, which argues that advanced ETCs would have colonized our galaxy long ago, hence they do not exist, Sagan and Newman postulated that interstellar exploration is a matter of diffusion. Jeffrey Landis argued the same sentiments in his 1993 paper titled The Fermi Paradox, an approach based on percolation theory, where he argues that the laws of physics impose limits on interstellar growth. According to Landis, there is no uniformity of motive to be expected from extraterrestrial civilizations. He said, since it is possible, given a large enough number of extraterrestrial civilizations, one or more would have certainly undertaken to do so, possibly for motives unknowable to us. Colonization will take an extremely long time and will be very expensive. It's quite reasonable to suppose that not all civilizations will be interested in making such a large expenditure for a payoff far in the future. Human society consists of a mixture of cultures which explore and colonize, sometimes over extremely large distances, and cultures which have no interest in doing so. Similarly, Professor Adam Frank and colleagues from NASA's Nexus for Exoplanetary System Sciences, NEXUS for short, wrote a paper in 2019 titled The Fermi Paradox and the Aurora Effect, Exocivilization Settlements, Expansion, and Steady States. Inspired by the 2015 novel Aurora by Kim Stanley Robinson, they argued that the interstellar settlement would occur in clusters, since not all potentially habitable planets would be hospitable to an alien species. In short, the laws of physics, biology, and evolution impose limits on how far and how fast a species can settle our galaxy. Solve for the T and H. To constrain those limits, the team considered the three main cosmological models of the universe, including static, matter-dominated, and dark energy-dominated. A static universe, as originally described by Einstein and his cosmological constant, is infinite in terms of space and time and is neither expanding nor contracting. A matter-dominated universe described the state of union of the universe prior to 9.8 billion years ago after the Big Bang, a time when the energy density of matter exceeded both the energy density of radiation and the vacuum energy density. A dark energy-dominated universe describes the latest phase of cosmic evolution, which began roughly 9.8 billion years ago, and is characterized by an accelerated rate of expansion. The team also considered all three scenarios in terms of logistic growth function to determine the number of planets settled with time, and from this, the team obtained the two parameters of their study. T, the time needed to settle a spherical section of an ideal universe that is both homogeneous and isotropic, and H, the Hubble parameter that describes the rate of cosmic expansion, aka the Hubble law or Hubble-Lemaitre law. For a static universe, they found that settlement follows the LGF, similar to how population growth, the spread of infectious disease, and chemical reactions do. As they noted in their study, these dynamical systems follow a general pattern beginning with a relatively slow start due to limited sources, in this case, habitable planets. But as they continue to expand and acquire new sources, this multiplies the number of available and propagation speeds up. This continues until the number of sources begins to dwindle and or the elements of the system are exhausted. To their surprise, the team noted similar behaviors when looking at a matter-dominated and dark energy universe, as Dr. Alinea told Universe Today via email. Remarkably, when the space itself is expanding as in the dark energy and matter-dominated universes, the process of settlement for the most part still follows the logistic growth function. We did not expect this result because the system with expanding space appeared to us as vastly different from a static system. Most of the studies we know on percolation are based on static lattice, e.g. spread of forest fire, propagation of disease, information diffusion, where the logistic growth behavior is usually observed. Our study extends this behavior to cases where the lattice is expanding like our very own universe, she said. Nevertheless, they did find that there was a delay in an expanding universe in terms of the rate of settlement compared to a static one. For a dark energy-dominated universe, they found that the total settlement time T was marked with divergence for a large enough expansion rate H. In accordance with Hubble's law, when H is large enough, some planets would expand beyond the horizon and become unreachable, of course. The essence, distant planets can be receding faster than the speed of light, making it impossible that an expanding civilization would ever reach them. They also found that in cases where the Hubble sphere H was smaller, the relation between T and H was linear. In other words, T was roughly equal to H. For a matter-dominated universe, their findings indicated that where H was similarly small, the same relation applied, but where H became larger, the relation changed significantly to T equals H2. In comparison to that of the dark energy-dominated universe, T did not increase exponentially or reach infinity unless H was infinite, said Alinea. So this is interesting because a matter-dominated universe is also characterized by a horizon. It means that for planets far enough from a reference planet in this universe, they are receding at a velocity faster than light, making it appear that they are unreachable. However, for a material-dominated universe, in accordance with Friedman equation, the co-moving Hubble sphere is shrinking instead of expanding. Put simply and informally, those planets far away from a reference planet in this universe that are initially moving faster than the speed of light are slowing down, making them reachable, at least in principle. So where are they? From their results, the team determined that advanced civilizations will generally follow a growth trend that is slow to start but will take off over time, eventually slowing and stopping as the number of reachable planets is exhausted. As Dr. Alinel described, this model is marked by a three-phase pattern: slow settlement rate, fast settlement rate, slow settlement rate. The question remains, what does this mean for Fermi's time-honored question? Where is everybody? How does this three-phase pattern help us refine the search for advanced civilizations expanding across the galaxy? To that, the team concludes that our galaxy may currently be in phase 1, characterized by a slow settlement rate. This could be because only a few intelligent advanced civilizations are engaged in interstellar settlement right now. This slow phase can be exacerbated by large distances between living planets. But once some number of traveling civilizations is reached, we may enter phase 2, characterized by a fast settlement rate. Given enough time upon entering this phase, we might finally say hello to aliens out there. Moreover, their results address the possibility of humanity becoming an interstellar species someday, perhaps as a means of ensuring the continued survival and development of our species. This represents a challenge in an ever-expanding, ever-accelerating universe dominated by dark energy. But as Dr. Alienil summarized, given enough technology to travel near the speed of light, it's still challenging to reach any planet in the universe, particularly the faraway planets. Having said this, there's a spherical section of the universe centered in our location whose planets are reachable, at least in principle, for possible settlement. Beyond this are planets that move away from us at a speed higher than that of light and may not be reachable. Unfortunately, this sphere is shrinking, so a section of the universe that we can inhabit, although large on a human scale, becomes smaller and smaller with time. If there is a mechanism to drive the universe to state such that its expansion rate is the same or similar to that of matter-dominated universe, then we would be lucky enough to have a universe that can, in principle, be colonized up to any distance from us. That is, the colonization and human influence in the universe is not bounded by any sphere, unlike that of dark energy-dominated universe. In summary, the answer to Fermi's question may be that advanced civilizations are in an early, slow phase of expansion that has so far prevented us from making contact. But as the spherical volume of Hubble space H that could occupy expands, we're more likely to get close enough to someone else that we'll finally know that we are not alone in the universe. Similarly, while dark energy may limit how far we can reach within our galaxy, not much farther, a sufficient volume of space would enable our continued development and could prevent a single cataclysmic fate from claiming all of our species. And who knows, perhaps cosmic expansion will not carry on as it has for the past 4 billion years, and the universe will slow down and achieve a sort of homeostasis, the kind Einstein preferred to believe in. In that case, our Hubble spheres may continue to expand indefinitely, and there will be no shortage of intermingling between cosmic civilizations. It does make for some exciting prospects, doesn't it? This was from Universe Today, the original article, and it's on Science Alert by Matt Williams from Universe Today. Please leave your comments, and thank you for your support. Please support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.